So basically for the past 3 weeks, no, not 3 weeks, 3 lectures, we've been talking about how the cache can be used to make sure that the access to DRAM is faster, right? Right now, we're going to talk about the other aspect of the memory hierarchy that everyone in the world right now is taking advantage of without actually knowing. This is called virtual memory. And so basically, we talk a little bit about what is virtual memory from the programmer's point of view, right? Uh, on Wednesday last week. And we basically said, okay, as a programmer, when I write a program, this is what I'll see. I have this abstraction that, hey, I'll have the memory that is unlimited. It's contiguous. Basically, when I call malloc, and let's say I malloc for 1 GB, right? I'm going to have the virtual address that is somehow 1 GB in length, right? But think about in the case that let's say I have multiple programs running on my machine at the same time with allocation, deallocation, allocation, deallocation. So basically the first program called malloc, 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 free. The second program called another malloc, 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 right? 3 mallocs for each program. What you would observe from the programmer point of view is I don't have to care about what the other program is doing. My program would work as long as malloc returns something that is not a null value, right? Malloc can return nulls when it actually don't have enough memory anymore to give it to you. But in most cases, you're gonna get some address and you don't have to worry about what the other programs are doing. The operating system and the hardware would both work together, right? In order to make sure that this abstraction hold in place. And one thing I want you to think about is when you buy a DRAM, let's say you shop for new desktop and new laptop, right? One thing you're gonna check is how much memory do I have, right? Is it 8 GB? Is it 16 GB? Be aware these things are physical. Basically, these are a physical thing that exists on your machine that you have to somehow manage, right? So what exactly is a virtual memory? Basically, when you run a program, when you call malloc, right? We've talked about an address, right? Malloc give you an address, pointer work with address. Every variable has its own address. Somehow, each of these addresses you got is an address that maps somewhere in the DRAM that you buy, right? And each process, each program, things like Google Chrome, Acrobat, Microsoft Word, Steam, for example, Discord, all these different processes has its own view of the virtual memory, right? These addresses are called virtual address. They have their own address. And these virtual address or VA, right? Sometimes we call this VA or virtual address. Physical address, we call it PA. There is a mapping between a virtual address to a physical address. So are you with me? Basically, for any given virtual address that you get, the address that you see in the C program that you're working on, and you have segfault and whatsoever, that address would be mapped to a physical address, a physical location in DRAM. And there's this thing called Memory Management Unit, or the MMU. What's the definition of management? Can someone tell me what does management mean? Yeah, it's managing, right? So one of your friends answered, management is someone who manages something. A management unit is a unit that manages memory. It's as simple as that. I have a virtual address. A manager should be able to tell what is my physical address, and that's actually one of the job of the MMU. It manages this translation, right? Translation means that I'm gonna translate the virtual address to physical address. So with this, we have two benefits that we talked about on last Wednesday. The first one is if I run an application, I have my own address. I have my own virtual space. Okay. The second benefit is because I have my own virtual space, and because my other application that runs alongside me also has their own virtual space, it means that the MMU can protect someone else from accessing my virtual space, right? Basically, this allows my virtual space to be protected from illegal accesses. As I said from last Wednesday, one of the quick example of this is segfault. When you are trying to access something illegal, the operating system tell you that, hey, that's not legal, segfault, I'm gonna crash this program. Right? So the third benefit is essentially you have a virtual view of unlimited memory. Right? What does it mean? So technically, when you buy DRAM, you know that you know the size of your memory, right? It can be 8 GB, it can be 16 GB, but there are ways to create this illusion that I have unlimited memory, right? If you have a data that you're not going to use a lot, these data can be kicked out from DRAM into a hard drive, right? And then you only maintain a frequently used data that stays in the main memory. So virtual address allows this mapping. Some of the mapping, as I said, you have virtual address that map to a physical address. You also have virtual address that maps to something in something like a block of data in hard drive to say, okay, it's not in the physical address anymore because you never use this data, so I'm going to kick this data out. It's in the hard drive already. This is done through a page table structure. So we're going to go into more detail now. So this is the recap of Wednesday. We're going to move on to the next set of topic, right? So please bear with me because there'll be new terminology. Right, there'll be new terminology. How many of you heard about the word page? P-A-G-E. What is a page of data? Anyone here have heard about this word before at all? Yes, no? No? Okay. Okay. Both type of answer. Awesome. So think of it this way. If I treat one address as a character, if I treat an address as a character in a book, right? What does the page contain in a book? I'm still in the book analogy. Let's say I have a book, and one address is basically a character. What is a page? It's a set of address. Awesome. Basically, yes, it's a collection of addresses that are next to each other, right? So if I have a page like this in a book, and then I say A, B, C, D, hello, right? And I just say that, okay, one address here is a character. The address for H is next to the address for E, which is also next to the address for L, right? And then they all stay in this page. And this page can be, as one of your friends suggests, this is swappable, right? You can put this page in hard drive. You can put this page in DRAM. Page access in both places, right? So let me kind of like formally define what's a page. Basically, a page is a range of address, and I don't know why that red text stays there. So let me erase. No, I can't erase this as well. Okay, PowerPoint bug. Basically, a page is a range of address. It is a range of address that are next to each other. It can be any size. By default, your computer right now they use 4 kilobyte. Basically, 4 kilobyte of addresses is within a page. It's mapped somewhere in DRAM or hard drive, right? Basically, it belongs somewhere. A program will see a virtual address and virtual pages. There's a concept of virtual address, which means that the virtual address would belong to some virtual pages. A virtual address mapped to physical address, which I explained already, right? So your VA, oops. Now PowerPoint is so buggy today, I don't know why. So basically you have virtual address that map to physical address. You also have virtual address mapped to this physical page. It belongs to some certain physical page in DRAM. Right? Any questions so far? Which is basically what's a page, what's an address? Any questions here so far before I move on to the next definition? All right, so we're gonna define another thing called page table. This is where we use the concept of indirection, which is also used in things like tree, linked list, right? Where you have pointers that point to the next item. This is the same thing. I will have a table. What's a table? When you start things in Excel, what does the table store? It's basically it's another collection of things, right? A table store a collection of things. A page table will store a collection of pages. So if you have a virtual page, right, that map to somewhere in DRAM, which is a physical page. So right now we need to separate out two concepts. Virtual, which is what the program sees, physical, which is what is on DRAM, what is already on in DRAM. So you have a virtual page that's mapped to the physical page. And because, as I said, virtually I want unlimited data, right? So there are going to be more virtual pages than the physical page. So the problem here is how can we tell where is the physical location of my virtual pages? Right? So animation bug here, but the idea is basically we can use indirection, which I'm gonna show in a bit. What we have or what we can have is you can have a table that store location of pages, or a table that store another location of the next level table, where each entry is basically store an address of the next level. So I'm gonna draw things here a bit, right? Because right now I'm sure this is a little bit confusing. Everything here is new. You have virtual address, right? Your virtual address would be used to look up the page table. So it would be used to look up the table, basically store the entry, the location of the page, right? So it would be used to look up which page do I, where, like basically which page store my data, because you have virtual address which map to some physical page. So let's say you have this we call this page table entry. So each thing in here is called page table entry. So this thing would point to physical page. And as I said earlier, how big is my physical page? So that's a good question. So basically, okay, let one thing at a time, because there are a few people asking the question on the chat. So there was a question about, does it mean that virtual address and physical address is the same? It's not the same value, but they point to the same data. Let's say you say in I, right? In I. Let me write the code just to be clear. Int I equal 10, right? what would happen if I do ampersand I? I get the address of I, right? Ampersand I would give me the address of I. That is a virtual address. So this gives me virtual address. Virtual address can be used to somehow get my physical address, which store, right, the value 10. The physical address actually store the value 10. Both virtual address can be, basically both virtual address and the physical address can be used to look up where is this data. The virtual address, to get the data, you need to translate the virtual address into the physical address before you can get to the data, the actual data 10. Then my other question is basically, what is a physical page? How big is that? It's 4 kilobytes, right? So how big is my address? Like basically, what am I pointing at? If let's say it's an integer, right? So that's 4 bytes. Basically, this is 4 kilobytes, which means that my virtual address point to some basically physical address over here, right here, that store the value 10. Like basically, you would need the virtual address to look up where is the correct entry, right? Correct entry that correspond to the page that I want to look at, and then you can go to the address. So this is called page table entry. Sorry, I write it on top of the text here. There will be another animation that hopefully is a little bit more clear. I actually draw it on PowerPoint and it looks way better than this. So here is the page table structure. As I said earlier, you can have the page, one single page table that points to the physical page. You can have multiple layers of the page table, right? Everyone here remember something called a tree, right? From the C lecture, that basically is a data structure that store the root, the next level, and the next level, and the next level. So you remember the tree structure, right? The tree as in data structure. The page table structure is also represented in a tree-like fashion. What does it mean? You have level 1, right? Let's say this is 4 kilobytes. If my address is 64 bits long, how many entries I can have here? So each one of this thing is 64 bit. And I have 4 kilobytes in total. So how many entries I can have here? But why is it 64 multiplied by 4? Okay, basically the number is 4098, right? Divide by 64 over 8, because this is in byte. We want to make sure we got in byte as well. This becomes 512. So I can have 512 entries. If I can have 512 entries, how many pages I can have? That's 4 kilobytes. Or do I did the math wrong? 10, 24, 2048. Yep, I did the math wrong for sure. This is basically 4 kilobytes. Four thousand 96, sort of 4096. It's 4 times 1024 for 4 kilobytes. Basically, it means that I have 512 of this, right? I have 512 of this. And let's say each one of them point to a page. So how much memory do I have here? If I have 512 in total entries, and I can point to different pages in DRAM, and then a page is 4 kilobytes. How many bytes of data do I have right now? Basically, you can have 512 multiplied by 4 kilobytes, right? And that's around how much? What's 512 multiplied by 4? 2 megabytes, right? So you have 2 megabytes. Okay, so my question right now, let's say I have this only one level of page table. Right? I have only one level of page table. I can only support 2 megabytes of data. Are you going to be sad when you buy 4 gigabytes of DRAM and then turns out I can only have 2 megabytes? The answer should be yes. Basically, you are overpaying for what you can handle. Right? So let's say you buy a 8 or 4 gigabytes of DRAM. What you want to do is to make sure that my system can support enough pages, can keep track of enough pages that would cover at least this 16 gigabyte or 32 gigabyte. So what do we do? Instead of this pointing to a page, right? What can you do is instead you have level 2 of the page table where each of these entry, instead of pointing to a page, it's not pointing to a page anymore, it points to another table. Each one of these entry points to a different table. I can't draw again. It points to another table. So how much memory can I support now? Basically, it's the number of entries over here, right? Over here on the level 1. Multiplied by the number of entries per table here on level 2, right? Multiplied by this. Multiplied by 4 kilobyte. So now with 2 levels, you can support. Yes, 512 multiplied by 512 multiplied by 4 kilobyte. Yes. Is it a lot better than 512 multiplied by 4 kilobyte? The answer should be yes. Basically, now you can support way more data. Anyone want to guess how many levels does your current machines goes to? You have a 64-bit machine, so it can go to more than 2 levels. Anyone want to take a guess on how many levels does it going down to? It actually go to 4 levels. So you have level 3 and then level 4. All right. So this is a x86 64. It's a whoops. Fat finger, sorry. x86 64. The 64-bit machine go to 4 level. With this, a virtual address which come in here, your virtual address, right, comes in here, will get indexed somewhere in this table, right? And now when you're over here, you get the physical page. Which then give you the physical address. You go through 4 levels of this, you get the physical address. Any questions so far about how you can get from the virtual address to the physical address? This is a high level concept. I'm gonna go into the detail in a bit, right? So let's break down. Wait. Let's break down what does this all mean? Right? You have a virtual address. What does each of the bits in the address represent? Because as I said earlier, you have an address, right? Think of it as the address tell someone how can someone find you, right? In our everyday life, if you have an address, someone can find where I am. They can find my home, right? What does the address in everyday life, right? This big address, what does it have? It would have the city, right? The city, which is like กรุงเทพ นครปฐม นนทบุรี or whatever, right? The city. The what's the English word for Kate or อำเภอ but yeah, so basically you have a bigger level, go down, 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 and then at the end of the day, you can pinpoint to the exact house, right? So the virtual address has the same concept. Think of it this way. Yeah, district. Good. Thank you so much for giving me the English translation for Kate or อำเภอ but yeah, you have the city. Each city contains multiple districts. Right? Multiple district contains multiple road. Multiple road contains multiple home addresses. You can think of the higher level page table. The first level becomes the city. The city give you then the second level page table, which then you use the district, right? To identify where you are. From the district, you have the street. The street name give you the entry inside the third level of the page table, which then you're gonna have the home address. That's when you can find the actual location, the physical location of someone's home. Virtual address works the same way. The lower bits, this is called page offset. Right? This represents the location of the address inside a page. Inside a page. This page offset tells you which byte inside the page you're looking at. The next level of bits would be used to index into a page table. Based on the caching lecture, what does index mean? It has the same meaning. What does it mean by index into the page table? So what does the page table look like? It's a table, right? So it has multiple entries. This can be indexed by the 0 entry, the first, the second, the third, the fourth entry, fifth, sixth, blah, 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 right? The index means that I'm gonna be able to tell, do I look here? Or do I look here? Or do I look here? Based on the value of these index bits, right? So let me give you an example of page table structure in x86, right? As I said, it's organized in a tree structure. All of these pages are stored in the main memory, right? Right now, your current processor uses 4 levels. The root points to the first level. That first table that you're going to refer to that has the index, the index from the virtual address. Then you get the page table entry, which tell you the location of my second level. So you can use the virtual address and the data from the first level structure to point to the second level. Each page table is a page table, it store a page table entry that behave like a tag, right? That provide information on where is the next level of the page table. And there's new terminology here because like all these bullets are recap of what I just said. The new terminology is called page walk. Page walk is the process of going through the page table to get your physical address. So let's do an example of a 32-bit x86, the old machine. Those Pentium like processor, that you can buy 10 or 15 years ago. They use 32-bit machine. Why do I use this example? Because it's simpler. It's used only 2 levels, where each page table can contain multiple page entries, right? Again, each entry, as I said earlier, it contains a pointer to the next level page table plus multiple special bits. Anyone here want to guess what bits do the OS check to give you segfault? The segmentation fault that you see when you run a program. What are the possible bits here that can cause a segfault? This is one of them, right? Somehow maybe you try to refer to an address owned by the admin, and the OS is basically to tell you like, okay, you did not own that address, segfault. So assume 32-bit machine. If you have 2 level page table and a page size is 4 kilobyte, how many bits do I need for the page offset? Remember, the page offset tell me which byte am I trying to access inside the page. So how many bytes do I need for the page offset? How many bits? How many bytes? How many bits? I think how many bits is a little bit easier. It's a log2 of, I need to be able to tell each individual byte inside the 4 kilobyte region. So how many bits do I need here? Log2 of 4K, right? Because that's the size that I have. I have 4 kilobytes. I need to be able to access each individual byte, which means that I need 12 bits. I need 12 bits for the page offset. The same calculation as when you do this caching, right? And because I have 2 levels, if I use 12 bits already, how many bits do I have left? 20, right? You have 32-bit machine. You already used the last 12 bits for the page offset, which means that you would left with 20 bits, and you have 2 levels. So it means that you can actually split them in half and half, right? 10 bits go for the first level, another 10 into the next level. So here's an example. As I said, you have 32 bits, right? The last 12 bits, bit 0 to bit 11, they are page offset. If I have 10 bits, how many entries can I have inside a page table? So okay, that's a great question. So one of your friends is asking that, okay, if there are 4 levels, how many bits would it need? Depends on how you would want the structure of the page table, but with the 64-bit machine, you have 64-bit in total, right? Let's say you use 4 kilobyte page, it means that the last 12 bits again is for the page offset. You are left with 52 bits. You can split that 52-bit based on whatever you want with it. Really obvious way to split it is split them equally, right? So you get 13, 13, 13, 13. These would be specified on the ISA manual. So if you go to Intel website, they will tell exactly how they split these bits into different page table levels. And that's a great question. Basically, if there are 4 levels, then you need to split each of the bits for the level 1, level 2, level 3, level 4, and then the page offset. Because the for level is for the 64-bit machine, you have more bits for the address. So your virtual address is now 64 bits, so you actually have more things. All right, so does it answer your question? So the direct answer is that depends on the manual. Like if you read the Intel ISA manual, they will say one thing. That's another great question. For the page offset, do we always need 12 bits? No, that depends on the size. It depends on the size of my page. Right now, I assume that it's 4 kilobytes. So if I need to be able to access each individual address in those 4 kilobyte region, then I need log of 4K, which is 12 bits. In Linux, you can actually set it to 2 megabytes. If you have 2 megabytes, then you would then need how many bits? Log 2 of 2 megabytes, which is 21, right? So it depends on the size of the page. The page offset, essentially, you just need enough bit to tell each individual location inside the page. All right. So over here from this example, let's say I have 10 bits for level 1 and level 2. How many entries I can have for level 1 page table? I have 10 bits. I have 10 bits, which means that I can specify 2 to the 10, right? 2 to the 10 different locations, which means that my table can have 2 to the 10 entries. Entry 0 to entry to 1023, right? Because it starts from 0. I have 1024 entry from PTE 0 to PTE 1023. So let's say my index bit is the level 1 here. Let's say my index bit is 0, 0. 1, 1. So that's 10 bits, right? So let's say that's my index bit 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. Which PTE am I pointing at? Which PTE am I pointing at here from this table? PTE3, actually, because basically you translate directly the index. Right now, the index bits for level 1 is 1, 1, right? What is 1, 1, 3? So you point to PTE3, right? And now what happened is, whatever value this PTE3 is, it would give you the base of the next table. So let's say PTE3 point to 0x FF 0, this is where this new table is in DRAM. It starts at 0x FF 0. All right. So if my level 2 index bit is 0, 0, 0, 0, 1, 0, 0, which of these entries am I pointing at? PTE4, right? One more quick question. Let's say each of these entry is 32 bits. What is the address of PTE4? Each one of these entry is 32 bits. What is the address of PTE4? Go back one step. What is the address of PTE0? Yeah, sure. So the question is kind of repeat this part. Basically, let's say the PTE3 here, the one here, say, okay, the value of PTE3 is 0xFF00. That tell me the base address of the next level page table, right? So let's say it's S0xFF00, which is represented here on the next level. What is the address of PTE0 on this table? What's the address of this guy here? It should be 0xFF00, right? Yep, it should be the same address. Basically, you think of it as everything here is in DRAM, right? Everything here is in DRAM. So if PTE3 point to 0xFF00, that's where my page table is. And this based on this structure, the first entry, you have 0xFF00 plus 0. That's the address of PTE0. What is the address of PTE1? 0xFF04, right? Because each one of these PTE is 4 bytes. It's 32-bit machine. What's 32 divided by 8? That's 4 bytes, right? Each one of these is 4 bytes. So PTE1 is at 0xFF04. PTE2 is at 0xFF08. PTE3 is at 0xFF0C, right? 10, maybe. Nope, 0B. So what is the address of PTE4? What is the address of PTE4? I think it's 0xFF10. You need to add 16, not 15. If you add 16 to 0xFF0F is FF10. My bad. All right, so this is the address of PTE4. So if my address is 00, I mean this index bit here is 00000000100. That points to what's 100? That's 4, right? So it points to PTE4. That's the address of PTE4. Okay. A 32-bit machine has only 2 levels, right? 32-bit machine only have 2 levels. What you can do is to get the physical address, this is what you do. Whatever value is here, whatever the value is on PTE4, whatever that value is, goes to this part, and then you take page offset, plug it here. Basically, you take the page offset, the last 12 bits, right? And then you take whatever PTE4 is there, attach them to each other. That's your physical address. Any questions here? All right, so my next question, let's say that this whole thing is 32 bits. How many bits do I have for the status bit over here? How many bits do I have? So the way you can calculate it is, right now you know that this is 12 bits, right? How many bits do I need here? It's 20, right? Why is that 20? Basically, the whole thing is 32 bits. 12 of those come from the offset. The other 32 minus 12 would be coming from PTE4. So this is 20 bits. Which means that this thing is 20 bits. Right? So this status bit is 12 bits. All right. You might have a lot of questions right now. we're going to basically there'll be in class exercise for this. Hopefully I think at the end of the day, hopefully these in class exercise I'm gonna come up for Wednesday helps understanding this example. The status bit, you remember the read and write. So let me go back from like basically let me go back in the presentation. I know it's a bad thing because it can confuse you, but these are the status bit. It tells whether you have the page in memory or not. It can tell whether you have the read and write permission, which can trigger segmentation fault as well. Let's say you want to write into some location that's read only. The OS will tell you you can't write into that location. You can have different flags, such as the access bits. The access bit basically tell that okay, someone accessed this page at certain time. These help the OS to figure out which page should be kicked out to hard drive and which page should stay in memory. The dirty bits, which means that someone modified the data. The global bits means that this is not shared. Everyone can use it. And then there's also spare bit where you can define whatever you want depending on the handshake between hardware and OS. Right. So these are the status bits which go into this part of the virtual memory, the part that are toward the right that says status 0, status 1, status 2. It just basically tell what is the property of my page, who owns it, can you read into the page, can you write into that page, what's the last time you accessed this page, has someone written something over that page or not, and then any additional bits that you can add that can maybe use to improve the performance of the system. All right, so let's do some example. Let's assume a two-level page table, 4 kilobyte page size, 32-bit address. Without the example I showed earlier, which is the exact same thing, how many bits do I need for the page offset here? This should be a given. I just want to make sure you're awake. What's the answer here? How many bits? Yep, 12 bits. Why is it 12 bits? Okay, the other one your friend answered log of 32. Actually, it's not log of 32, it's log of 4K. So you need 12 bits. How many page table entries are in the page table? If you have two levels, 32-bit address, and then 12 bits is already used for the offset. So how many page table entries, grammar, page table entries would be inside one page table? So you have how many left, right? So you use 12 bits already. In total, you have 32 bits. You have two levels. You can use 20 bits, the remaining 20 bits for each of the level. For both two levels. So for each of the level, how many do you have? 10 bits. How many entries you can have given that you only have 10 bits? 1024. Yep. So you can have up to 1024 per entries per page table. All right. Let me give one more question. With a 32-bit address, what's the size of DRAM can I support? With these setup? This was on the exam last time I teach it. But given from this information, you should be able to tell. So how many entries are per level, per page inside a page table per level? How many entries do you have? 1024, right? 1024 entries. How many levels do you have in total? There are 2 levels, right? So how many pages can I support with 2 levels than 1024 entries per level? So how many pages can I have? Why 512? Is it because of my earlier example that said 512? Okay, so let me go through this for you, right? You in the first level, you have 1024 entries, right? Each of these entry points to somewhere what? Huh? Nope. uh, so let me do this calculation. The easiest way is to figure out how many pages do I have, right? The first level can have 1024 entries. Each entry points to a different table in the second level, right? Each entry here points to another level. Yes. So the other answer on the chart is 1024 multiplied by the second level. You have 1024 entries as well, right? So you have the first level, 1024, second level, you also have 1024. That's the amount of pages that you can support. So you can basically support these many pages. And how big is one page? 4 kilobyte, right? So you can support 1024 multiplied by 1024 multiplied by 4 kilobyte. That's 4 gigabyte. All right. So if you buy a desktop nowadays, will you ever use the 32-bit machine or install the 32-bit version of Windows and Linux? And I hope your answer is no. I'm gonna use 64 bits, right? Because basically, because if you use 32 bits, you can't use all the RAM that you have that you buy. Uh, so this is actually one of the reasons why people migrate. So if you look at how long ago? About 10 years ago, where we transitioned from 32-bit to 64 bits. I'm not sure if you remember those days. I'm like you were still really young during those time. We used to use 32-bit version of Windows. We used to use 32-bit version of Mac and Ubuntu and Linux. Then suddenly the hardware technology improved, right? So you can buy 8 gigabytes of DRAM, which means that there is a shift from 32-bit to 64-bit. And nowadays, everyone uses 64-bit machine. With 64-bit machine, we need to talk about this, the performance overhead. One thing you need to be aware of is the page table, the one that you said, hey, we look up this page table. Those are in DRAM. And what do we learn about DRAM? One thing we learned from the caching lecture is DRAM is slow, right? DRAM is slow compared to the cache. So based on our caching lecture, hopefully by this point you roughly know that hey, DRAM is not as fast as it can be. You want DRAM to be faster. That's why you have the cache. But let's say you need to go through the page table structure and you are using a 64-bit machine. how many DRAM lookup, how many DRAM access do you need just to get your physical address? How many trips to DRAM do I need to get the physical address of a 64-bit machine? Remember, you have 4 levels, right? So you need to go to the first level, that's one time, second level, third level, and the fourth level, which means that you need to go to DRAM 4 times, just to know where your data is. Are you with me? Basically, just to go access your data, you need to go to DRAM 4 times. So quiet right now. Are you with me? Say yes or no. Do I need to explain it again? Okay, at least there's one yes. Okay, at least there's one of you with me right now. Basically, these page table structure is in DRAM. So when you do translation from virtual address to physical address, you need to go to DRAM multiple times. And this is a big overhead, right? Because in right now, all your machine use 4 level of page table. Problem 1, you can't access DRAM to grab your data without knowing the physical address. Because if you don't know the physical address, you can't do anything, which means you need to go through 4 level of page table to get your physical address, and then you can go the 5th time to get your data. That's 5 trips, right? The second problem, this is the most concerning problem about the virtual memory and performance overhead, is right now on your computer, you cannot access the cache without knowing the physical address. We'll actually go in depth on why. But what does this mean? What does the fact that if you don't have the physical address, you can't access the cache? What does it mean to the cache access then? So let's say I want to access the L1 cache, right? But I don't know what's my physical address. So to access L1 cache without knowing the physical address, how many access to DRAM? Yeah, so one of your friends is asking me this question. So in a 64-bit machine, to get the physical address, do we need the value of level 4 along with the page offset? Yes. Basically, you need the value of level 4. To get the value of level 4, you need the value of level 3, which means you also need the value of level 2, which means you need the value of level 1. The process is you have the virtual address, get the value of level 1, then level 2, then level 3, and then level 4, and that's when you get the physical address. Right? Which basically partially answer this question, which is, if I want to access the cache, which is designed to make sure that you never need to go to the main memory, right? Your data is in the cache, you don't have to get the data from the main memory. If you have virtual address, you cannot. Because you have virtual address, but you need physical address to access the cache. As I said, I'll tell you the reason why. But with this constraint, it means that you need to go to the memory 4 times to get your physical address, just so that you can access the cache. And is that bad? Or that's a bad thing, right? Basically, you don't want this. Anyone want to take a quick guess of what do we do to fix this problem? So we use the cache to basically cache data inside this L1, L2, and L3 caches, right? To make sure I can get my data quicker. So what can you do with the physical address? Yes, that's a great answer. Basically, that's a solution. You keep the data, you keep the physical address data. Well, yes, that's another separate paper about keep the level information inside the cache. But one thing you can do is keep the physical page information inside a caching structure, right? So yeah, so you can cache them. Basically, you use cache to cache the physical address. You use cache to cache the data. You actually, that's another separate cache to cache the instruction. So right now in your processor, when you buy a laptop, when you buy a desktop, in every single laptop and desktop these days, there is a cache for your data. There's a cache for your address. There's a cache for your instruction. Is used everywhere. We'll go into detail in the next lecture on Wednesday on what is the name of this cache and how do we use it. And why is it so important that this cache is well managed? And then, how many of you use virtual machine and hate the fact that it's so slow? Or how many of you realize that when you have a virtual box opening up and it's super slow? One of the main reasons is actually virtual memory. And I'll tell you why in the future. But the reason why is instead of 4 access to DRAM, you ended up doing 24 access to DRAM inside your virtual machine. And that's actually one of the big reasons why virtual machine is so slow. All right. There are actually many things you can do to kind of improve this, but you might have realized still not perfect. You can use Docker. It's not great, right? It's still kind of slow, but it's better than nothing. And there's a lot of benefit of using virtual machine. We'll go into detail on Wednesday and next week. Hopefully I now motivate why you might want to understand some of these, like why do we care about caching? Okay, so let me read the question. So there's a question saying, okay, as we need to access 4 level to get the PA for a 64-bit machine, does it make 64-bit machine slower than the 32-bit machine? That's a great question. That's a great question. The reason why is that, yes, it's actually make the translation slower, but at the same time, because you have way more DRAM, right? So you can support more than 4 gigabytes. Uh, that the fact that you can have more capacity make it faster. So at the end of the day, if you manage this caching for physical address well enough that you don't have to do page walk that many times, you are not going to face that problem that many times. So yes, the answer is yes, it's going to be a little bit slower. This is a big reason why NVIDIA kind of cheat their way on virtual memory on GPU. If you're interested, I'll probably talk about it toward the end of this class just because that's my thesis topic, right? So designing virtual memory for GPU is like one of the things I do as a PhD, and I kind of like propose like one of the first system that supported in a more realistic way compared to what NVIDIA is doing nowadays. So I'm going to talk about that. This particular question, which is like, okay, if you have a 32-bit machine, isn't that better? Uh, yes, in the sense of translation, but no, because at the same time you lose capacity, you lose the ability to support large DRAM. And with the program that you use nowadays, all this quote unquote, I'm gonna use keyword here, the big data, machine learning, they need a lot of memory. So that's why like you can't use 32-bit machine anymore. Your program will be so slow because everything will go to hard drive, right? So at the end of the day, you need 64-bit machine to actually make sure to actually make sure you can still run them fast enough, then you need to manage the virtual memory well. So there's a lot more proposal about how to design new type of virtual memory. I actually have a paper that came up last month on one of the like top architecture conference that actually redesigned this whole thing. I'm not going to talk about that for sure. It's a little bit too in depth, but it is a really active area of research right now on like, okay, can we come up with a better virtual memory management? Because if you're using things like cloud, virtual machine, Docker, these whole thing affects how fast your program is, right? It gets like a lot more important compared to like 5 or 10 years ago. All right, so before we leave today, I want to give you a proper example on in class exercise 10, because I feel like a lot of you already attempt in class exercise 10, and there was a really great like discussion on the office hour about how this whole thing works. But let me kind of draw it out, right? Because that's quite a bit of a question, like questions about replacement, eviction, and all those things. So how many of you remember how many steps do we have in class 10? And how many ways? Okay, I assume that that's your answer, but you forgot to change the language. But yeah, 4 ways and 16 set. Yep, exactly. 4 ways, 16 sets. So hopefully I can draw 16. Nope, I don't think so. I think I will fail drawing 16 different things here. 1, 2, 3, 4, 5, 6. All right, I need one more line. On 2 more, I don't know. This is set 0, set 1, set 2, set 3. Nope, I need one more. So this is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's 15 set, right? This is 4 ways, so it's way 1. I'll just start from 0. Way 0, way 1, way 2, way 3. Let's go through the first loop. There are 2 loops in the program from the exercise. The loop basically do this: A of I equal I, B of I equal I, right? And then I go from 0 to 1024. Okay. For the A of I of 0 to 128, what happened? If you go through this example, you see that A0 to A7 would be in the first set. A8 to A15 will be on the second set. And then this will be all the A's, right? Up to A120 to A127. The B's will be here. Right? So what happened when I is 128? What happened when I is 128? Someone tell me, please. Yes, it maps to, so basically one of you answer it now map to set 0, which means it's going to way 2, right? Because way 2 is empty right now. So you have a 128 to, what's 128 plus 7? Sorry, 150, 135. A 136 to a 140. I can't do math. 43. Go down. Up to how much? What is the last set 15 here? At the same time, B is just here, right? 255. Yep. So it's A 240, 8. Is it 8? Yeah. 255, right? And then the B is 128 to B 135 would be here. Go down to B 248 to B 255. So what happened when I is 126? 256, my bad. What happened when I is 256? What does it do? What happened to set 0 of my cache? Kick out way 0 set 0. Yep, exactly. Basically, A256 would kick out A0 to A7. You all see that? And then B would kick out way 1, right? B would kick out way 1. So what's the hit rate here? If you do this carefully and you go through the loop, you'll see that hit rate is 7/8, right? Every 8 access, you bring in one cache block. And then, like for example, A0, and then A1, A2, A3, A4, A5, A6, A7 would be a hit because those is already in the cache. And the same would happen for the second loop, right? So the second loop, what we do is C of I equal A of I, right? Plus B of I. So what happened when I is 0? C0 equal A0 plus B0, right? So what happened here? Everyone kick everyone else, right? Right there, A0 is not in the cache anymore, B0 is not in the cache anymore, so you kick everything out. So what's the hit rate of the second loop? What's the hit rate of the second loop? Is it okay? Is it the same as the first loop where there's no cache hit when the first time I'm gonna see the block because it's already evicted, right? So you're gonna see 7, 8 as well. 7/8. So this part has been on a discussion on Wednesday during office hour. That's great. One thing that I want to make sure you are aware is you can write the code so that you can get better cache hit rate. Okay, so one of you were asking me, isn't from 256 onward no hit rate because it's thrashing? Actually, thrashing is bad, but it still make the hit rate 7, 8. The reason why is because when you bring in, say, A256, right? When you bring in A256, you actually bring in A256, 257, 258, 259, 260, 261, 262, and 263, right? You bring in 8 of them. inside the cache block because it's in the same cache block. A cache block is 64 bytes. So when an integer, over here, a cache block is 32 bytes, an integer is 4 bytes. So you bring in 8 different things. That's why for 256 to, I can't do math again, 256 to 263. Yeah, 263, those would have 1 cache miss and 7 cache hits because they are in the same cache block. So for throughout this iteration, you're gonna get 7, 8. My question is, can you do better than 7, 8 with the same program? I mean, basically, can you modify the program to get better than 7 over 8? Who want to say yes? I'm going to show you how, actually. So the answer is yes. You can actually write this program to actually get better hit rate. Let me give you one example. The original code is something like this, right? For I equals 0, I is less than 1024, I plus plus, right? And then you have AI equal I, BI equal I, right? That's the first loop. The second loop is basically for I equals 0, I is less than 1024, I plus plus C of I is A of I plus B of I. What's the easiest thing I can do here to make sure that I get way more much better hit rate? This is original code, right? One thing I can do here is I can merge them. So I have one loop for I can write again. PowerPoint for I is 0. I is less than 1024. I plus plus, right? A of I equal I. B of I equal I. And then C of I equal A of I plus B of I. Will this give me a better cache hit rate? Remember that the address, the one that deal with getting something from the main memory is the same. You have A of I right here, right? You have C of I right here, and then A of I, B of I right here. So there are 5 memory access. Some of them hit in a cache. Over here, you also have 5 of them. 1, 2, 3, 4, 5. 5 of them as well. But when you're on the line that say C of I equal A of I plus B of I, these two are guaranteed, right, to be in the cache. Why is that the case? Because you just used it earlier in the previous line. They will be in the cache, right? So can you see that this code will have better hit rate? How much better? What's the hit rate of this particular access to AFI? Is it 7.8 or 8.8? Any taker? Anyone want to take a risk here? 7, 8, yes. So even with the original cache for the second loop, we already have A and B in the cache. That's not the case because we go to 1024. It just happened that when you go to that high, you kick everything out. Right? Basically, you kick everything out. By the time you finish the first loop, A0 is not in DRAM anymore. I'm not in the cache anymore. They got kicked out by A256. So that's why it's 7, 8. So over here, it's also 7, 8. What's the hit rate of BI here? 7, 8, right? What's the hit rate of CI over here? It's the same thing. That's the first time you see C, right? So it's 7, 8. The interesting part is what is the hit rate of this AI, the second access to AFI? 8, 8. Yep. Wait, why is it 0? It's actually 8, 8, right? Because these put AI in the cache. Oh yeah, 0 miss rate. 0 miss rate is our hit. You everything here is a hit. So over here it's also 8, 8, right? 8, 8 hit rate, 0 miss rate. So what's the total hit rate here? So you have 7, 8, right? Plus 7, 8, plus 7, 8, plus 8, 8, plus 8, 8, 8. This whole thing, when you add it up and then you divide by 5, because you need to average across 5 of them. Yes, so for the original case, the second time will also 7, 8, because by the time you reach the second loop, the old data get kicked out. So you do it again and you get 7, 8. You can write a better version of this code and get how much? So that's 7, 7, 7, that's 21 plus 16, that's 37. So that's 37 over 8. 37 over 40. So this is basically 37 over 40. So that's a hit rate. That's actually better than 7, 8. Okay, so that's a great question. So one of you asked, why is it 8, 8 now? The reason why ALI and BLI, the second access is 8, 8, is because the previous line, the access AI, followed by access to BI, right? That two access would put AI and BI in the cache. We'll put AI and BI in a cache, right, for both of them. What is my next instruction? Getting AI and getting BI, right? My guarantee next instruction is get AI, get BI, add, write the result to CI, right? So the second time I need to access AI, the previous line would bring AI into the cache. That's why you get 8, 8. Because the second time you access AI, it's guaranteed that that's going to be in a cache. Because your previous instruction access the same thing, and that same thing will be in the cache. How does the index bits come into play? That's a great question. It comes into play in this particular scenario because we go through all the index bits. So we go to set 0 to set 15. So let me go back one slide here to the example here, right? Okay, let me answer the first question, which is like what does the index bit where does the index bit come into play? Basically, we don't have enough set. So A0, A128, A256, A128 multiplied by 3, whatever 300 something that value is, and A512, they all map to the same set. They all map to the same set. And because we only have 4 ways, they're going to kick each other out, right? By the time you finish the first loop, A0 would get kicked out, A128 would get kicked out, B0 would get kicked out, B128 would get kicked out. Because if you go through the loop and you check the set ID, that's how it's being mapped. Right? So with that, it tells you that even though the second loop use AI again, you're not gonna get the extra hits because it's going to be kicked out already from the cache. The other question is why do we have 4 ways and 16 bits only? 16 sets only. Oh, so that's my assumption. Basically, it's the assumption of the in-class exercise. In a realistic scenario, you have way more sets. If you write a simple program, it's pretty hard to have a cache miss. By simple program, I would say most program you see on the assignment, that doesn't include realistic workload that you see nowadays, where it actually deal with so much data that it's not in the cache anymore. All right, so does it answer your questions? Any other questions from this example? Okay, cool. So I'm gonna keep the for each loop all the way in a set. Yes. So once the value of i's is 256, it kicks out everything from there. And then when you are at 512, what do you mean by even if 128 don't get used? It get used when you read from it. Is the question when you kicking thing out, are you kicking the entire 4-way or 1-way? Is that the question you're asking here? I'm trying to understand the question, sorry. Okay. So when you have 4 ways and there's 5 things, look at this scenario. Let's say you're on a bus and there are four seats in total, right? And there are 5 people. Someone come in, you kick. If you want to replace someone who's on a chair, who's sitting on a chair, you replace only one person. You don't kick all 4 of them. That's rude, right? Basically, it's the same here for cash. You have one new item coming in, you pick out of those 4 who was not really take advantage of the cash and kick that block out, right? Which is, I guess, the same thing with the bus scenario. You have 4 seats, 5 people, you kick whoever is not taking advantage of the seat, I guess, and then ask that person, hey, can I sit there? So you replace 1 way at a time. 1 way at a time. You don't kick out everything. The policy that determine who get kicked out right now, our assumption for this class is called LRU, or least recently used, which is basically the block that has the last access, the furthest from where it is right now. Basically, that's how LRU is defined, least recently used. So if in that scenario, if 128 don't get used, and then everyone else on the 4-way get used, then 128 get kicked out. Think of it as every time you access something, you set a timer from 0, right? And it count the time up and keep counting and counting and counting. If you need to access this address again, you reset the timer it becomes 0 again, and it keeps counting up and up and up and up. When you need to replace something, you look at all the cache block and see who has the highest value for the timer. And that one gets kicked out. Basically, everyone has a timer who has the highest value get kicked out. But if you need to access and it's a cache hit, you reset the timer. Okay, so I think you understand. I think this is no. So I think your question is a little bit confusing because that's not really like what happened on the code. Basically, what you're asking is, let's say you have A0 to A7, right? A0 to A7 and then B0 to B7. What happened when you need to access A8, A9, A10? Is that the question? So yeah, A8 actually is mapped to set 1, so it will go to the set 1. It's not involved in set 0. So when you go to set 1, you only look at set 1. You don't look at the other cache block in the other set.